Okay, so as we said in our earlier classes, we will do the final presentations from each of you in the last week's lectures. And this week we'll have the homework 3 due, which was supposed to be due last week, but we postponed for 1 week since we were actually slow in our progress. So after this homework, you will have no more homework to submit, so you can focus on your report and final project. So the plan is that you will do the presentation, a short presentation, approximately 5 minutes in the last week, and then you'll submit your report 1 week after the week 10. So that will be during the finals week. So then you can plan ahead. And I will actually, so I think within this week, I will post the presentation order to our CCLE. So I think probably if the time will work for you, we could have all the presentations on one day instead of on 2 days, Tuesday and Thursday, but we'll see. So we will try to do the scheduling. And I think in the most fair way is to randomly shuffle the order. So everyone will present in a random order. So we're not favoring anyone for asking you to present earlier or later. Okay, so that's the plan. And today we're going to finish our discussion about a sample quantile. So we will basically give you some examples about what it actually means and how to use it. Okay, so first of all, let's restate the important result for sample quantile. This is from our last Thursday. So as a reminder, for the pth quantile, we have its sample version and we have its population version. This is the sample version or sample level versus population level difference is the theme of this class, or I would say the theme of statistical inference. So for the sample quantile, it's based on order statistic. It's defined as the order that is equal to the ceiling of n times p. Okay, this p is between 0 and 1. This is the pth sample quantile, and for the pth population quantile, we actually define or denote it as lowercase xp, and it is actually defined as f inverse p. And if you recall, f inverse is something we defined in our first lecture. Okay, so this is defined, if you recall, as the nth of x such that p is less or equal than fx. Okay, so this is how we define it as the quantile. And this inverse is naturally defined if this big F is a continuous function and invertible, right? So that is naturally defined. And this general definition is to deal with a case where we may have some discontinuity in our CDF. And sometimes we may not even have an X that is exactly, whose Fx is exactly equal to P. So in that case, this inequality becomes strictly less than, but still we want to pick the minimum X such that Fx is an upper bound on P. So this is a more general definition. And so by this definition, the quantile exists for any general F. Okay, so coming back to our important statement or conclusion about the asymptotic distribution of sample quantiles, we give the statement in the form of a corollary, and we actually talk about the joint distribution of two sample quantiles, the pth and the qth. So we'll write this as x and p minus xp, so sample quantile minus population quantile. This will converge in law to normal distribution with zero mean. So this is also two-dimensional 0. And the covariance matrix takes this form. So it's a P times 1 minus P over the density function evaluated at the population quantile squared. And this covariance is P times 1 minus Q, Fxp, Fxq. Okay, I copy it here. Fxp, Fxq. And finally, Q 1 minus Q, Fxq squared. Okay, so what does this mean? If we think about the variance term, that's very interesting. So the variance term for this pth quantile, okay, so basically what we have is the asymptotic variance of root n times x and p. Okay, of course we have this, but this is not really affecting the variance. It's not only affecting the mean. Is p times 1 minus p over fxp squared. So what does this imply? This implies that the larger the density, if this density goes up, then the asymptotic variance will go down. And why is this reasonable? If you think about what the density means. So from the perspective of calculus, right, this fxp times delta x, where delta x means the length of a very small interval around xp. This is approximately what? This is approximately that let me write it down. It is approximately that the probability that my xi is in this small neighborhood of xp. xp minus delta x over 2 to xp plus delta x over 2. This is by the definition of the probability density function. So we have that. So in other words, you see that basically this is, we can understand this as the proportion of observations in the small neighborhood of xp. Okay, so you see that the larger the density, the larger the proportion we would have in this small neighborhood. So naturally, we can have better accuracy in estimating the population quantile using the sample quantile. So that's why this density is playing a role here. It actually reflects how dense your data points are around this population quantile. So that will determine how good your sample quantile is an estimator. Okay, so this is the understanding behind this formula. Now let's apply this formula to the sample median and see what will be the asymptotic distribution. So when we set p equals to 1/2, this is what we call the median, okay? So of course, here we have two median, population median and sample median. And by plugging the p equals 1/2 into this formula, okay? And also let's look at a special case, normal distribution. Let's say x1 to xn are from IID from a one-dimensional normal distribution with mean mu sigma squared. And then we will be able to write down the density of this normal distribution at the population median. Okay, so when p equals 1/2, the population median in this case, in the normal case, is of course equal to mu. That's the population median. And then if we want to evaluate the density of normal distribution at the population median, F mu, we can actually see it's equal to 1 over root 2 pi sigma. You can verify this. The exponential term becomes 1 because that exponent becomes 0. Okay, then we use this formula to derive the sample median's asymptotic distribution in this special case. We can actually write as root n. So the sample median still has this form. The order statistic as the sitting of n over 2 minus the population median. And this is converging in law to normal distribution 0 mean. And the variance, it will be equal to 1/2 times 1 minus 1/2 times F mu squared by our formula. And by simple calculation, we can see this is just equal to 0 to pi sigma squared, pi sigma squared over 2. That is the asymptotic variance of the left-hand side. And if you recall, we can compare this sample median as an estimator to the sample mean estimator, because sample mean is also an estimator for the same mu. Mu is both the population median and the population mean of the normal distribution. So if we compare this to what we have from the central limit theorem about sample mean, xn bar minus mu. Okay, that will give me 0 sigma squared by central limit theorem. So which one has a larger asymptotic variance? It is clear that the sample median has a larger one because pi over 2 is greater than 1. So what this suggests is that asymptotically, the sample median is not as efficient as sample mean. Is less efficient than sample mean asymptotically. Okay. And one more thing we can interpret about this result is that we know the asymptotic variance, if you think about, so let's forget about the convergence, okay? But you divide this root n to the right-hand side, then this root n will become n that will go to the denominator of the variance. So you know that the variance term is on the order of 1 over n, right? So that's something we know. And we know it's, so in other words, variance is inverse, is inverse in n. So the larger the n, the smaller the variance. And what is pi over 2 over here? So you can think about it, or we can write it another way. So 2 over pi is approximately 0.64. So you can interpret this as, so given that the variance of sample mean is only 64% of the variance of sample median. So we can say that the using the sample median as an estimator, the effective sample size is only 64% of n. So this suggests that the sample median has an effective sample size of 64% n. So why do we say this? The reason is that if you think about the asymptotic variance, with only 64% of the sample size, the asymptotic variance of my sample mean would be equal to the asymptotic variance of sample median based on sample size n. So that means that compared to the sample mean, the effective sample size of sample median is only 64% of n. Okay, so that's application of this result to sample median. Okay, now further, let's look at a concrete example where our data comes from a Cauchy distribution. Okay, a further example, let's say that our x1 to xn, they are IID from a Cauchy distribution. You know, a very important property of Cauchy distribution is that it doesn't have moments. If you do integration to calculate expectation and the expectation of the square, they do not exist. But we still have the density. The density function will allow us to calculate the population quantiles. So even though this density doesn't have moments, it has quantiles. So the density is with density or PDF as fx equal to, the constant is 1 over pi sigma, and x is in the second term, 1 plus x minus mu over sigma squared. Okay, that's the Cauchy density, and the x is still defined on the real line. So what we know about this is that the population quantiles are well defined. So we would know the population first quartile is actually mu minus sigma, and the population median is actually mu. It's still centered at mu. And the population third quartile is mu plus sigma. So in other words, this sigma here cannot be called as the variance because this distribution doesn't have any moments. But this sigma also has its meaning. So the sigma is actually the length of the half of the length of the interquartile range, right? Interquartile is defined from the first quartile to the third quartile. And mean is the center or the median. So here we can say the mu is the median, but it's not the mean. The mean variance do not exist for Cauchy distribution. Sigma is equal to the, which we can call this as the so basically this is a term we can borrow. It's called a semi-interquartile range. Okay, and this here is not a standard deviation. We do not have standard deviation. So if we want to estimate the mean, to estimate the median mu and the semi-interquartile range sigma, we can use the the corresponding sample quantiles for estimation. So in other words, you see a natural thing to do the estimation is to estimate mu hat by the sample median. Okay, and we can estimate sigma by the difference between the sample third quartile minus the sample first quartile divided by 2. That will be my estimators. And their asymptotic distributions can be derived from our result. So without giving you the detail, I'm just going to give you the result. So by applying that corollary, and for this part, to derive the asymptotic distribution for sigma hat, we need to use Cramer's theorem and apply the Cramer's theorem to the joint asymptotic distribution of the first quartile and the third quartile. Okay, so but something very interesting is that, so after applying, let's say, apply the corollary and Cramer's theorem, we'll obtain those two results. The first one is about the sample median minus mu. This is converging in law to normal distribution, mean 0, variance term pi sigma square over 4. And for the sigma hat, okay, minus sigma is converging in law. And interestingly, by algebra, we've actually found this as equal to 0. But here there is some difference. I think, yeah, let me see. Am I right or wrong? Right, I think there was a typo. I mean, I need to make the correction in the notes. So this should be pi square, sorry. Yeah, so it's pi square sigma square over 4. So the interesting thing is that these two things have the same asymptotic variance, but this is just a coincidence by the algebra that gave us this result. And again, you can verify that. So if you compare this to the Gaussian case, where in Gaussian, you can estimate mu, right over there, that is the mean. You can estimate mu by the sample mean. And for the sigma, you can estimate that by the sample standard deviation. You can do those for Gaussian distribution, and that will actually be more efficient than those two things. So using the sample quantile asymptotically is never as efficient as you use the sample mean or the sample moments. But we know that in practice, the sample quantiles are called robust statistics, while the sample moments are not. And the reason of that is because the sample quantiles are robust to outliers. So you see this a double-sided blade. You have on the one hand, sample moments in the calculation, you essentially use all the observations. So that makes the sample size large, being more efficient. But on the other hand, using all the observations suggests that you are not immune to outliers, right? If you just make some outliers to your observations, you will still use them, and your result, your estimator will be affected by them. But the sample quantile, on the other hand, is based on order statistic. And when you use order statistic, only the order related to your quantile, related to the P, the probability you're interested in, that will be of your concern. So any observations further away from that order statistic will not be used. So that makes it more robust to the existence of outliers that are extremely large or extremely small, right? They are not going to affect the order statistic in the middle. But on the other hand, what you lose is that you lose the whole sample size. You're only using the sample size concentrated around the quantile you're interested in. So everything has a trade-off. Okay, so that's all I want to say about the sample quantile. Do we have questions before we move on to our next topic? Okay, so that's good. So our next topic is getting more abstract. So I'm going to say that first. It's getting more abstract, but you can think about it as a way that we generalize what we have said before about the sample moments, okay? So this is what we call Use Statistics. Okay, and here the U stands for unbiased. Okay, so you can think about a special case of Use Statistic is the unbiased version of sample variance. Okay, so this one, the thing we're familiar with. This is an unbiased statistic. And because naturally we will do 1 over n instead of 1 over n minus 1, right? And this 1 over n minus 1 is for bias correction. So, but before we introduce the U statistic, we'll start with what we call V statistic. Here the V is from a statistician and mathematician, Richard. So I think it's a German name. So I think the German pronunciation should be von Mises. But I think in American people pronounce this as von. So this V comes from his last name. And so this von Mises statistic is a class of statistic that generalize our sample moments. Okay, so you can consider this as if we just think about the V statistic, then we will write it this way. Let me see. Yeah, probably I'm not going to write it in case this is a little more complicated than that. But anyway, so this, you can think about this as the generalization of sample moments. And we will see where the generalization is. Okay, so before we talk about the V statistic, we need to give you a definition or a concept called statistical functionals. So what do we mean by a functional? You can think about functional as a generalization of function. So, but when we say functional, the domain of a functional is no longer defined as is no longer a subset of the n-dimensional Euclidean space or the n-dimensional complex space. So now we can generalize to any space. That can be the domain. And so in the very specific way here, when we say statistical functional, okay, we denote this by T. It actually maps from a set of distributions to the real numbers. So in other words, this is a set of CDFs. It maps from this to real values. So you can think of the input or argument of a functional as a CDF, and the output or the value of the functional as a real number. And this is very aligned with definition of functionals. Here, statistical means that this adjective statistical means that the domain of this functional is a set of CDFs. So let me give you some examples of statistical functionals. So first one, we can actually consider the CDF function evaluated at a particular value being a statistical functional. Okay, so the first example is, let's define, okay, the argument f is a CDF. Define it as its evaluation at a constant C. Okay, this is exactly a statistical functional. The input is a CDF, the output is a real number between 0 and 1. Okay, so in this case, we can actually write it as the probability that a random variable y following CDFF is less or equal than C. Okay, so this notation means that y follows the distribution f. So from now on, I'm going to make a distinction. The distinction is that we are going to use x1 to xn as random variables representing my data, representing my sample, or now we call it data. So they are the random variable notation for n numbers or n data points I have. And this Y notation is going to be used for a general notation for a random variable that follows some distribution I'm going to specify. So this is a general random variable following a specific distribution. And you will soon see why this distinction is very important. Okay, this is a functional. And now I have a question. Since I already introduced this sample, right? Sample notation. So from our previous lectures, we already know that we can define an empirical CDF based on my sample, if you recall that. We can have this Fn hat. That's the notation. And that's the empirical CDF, eCDF, right? How do we define it, if you recall? This Fn hat evaluated at x is defined as the proportion of my observations less or equal than this x. That's the definition of the empirical CDF. So now you see, I can have an interesting idea. That is, what if I plug in this empirical CDF to replace the true CDF, the population CDF? You see, if I do this, this becomes what? Based on the same definition, I'm just writing along. So everywhere when F appears, I replace it by F hat. So now you see the reason why I need a general notation for Y. So in this notation, it means that my Y follows the empirical CDF. And I'm interested in, for such Y, what is its probability being less or equal than C? You can see that here, for this Y, empirical CDF means that Y has probability 1 over n at each xi. This is what the empirical CDF means. It's a discrete distribution with n values at x1 to xn. When we say Y follows the eCDF, Y is taking that discrete distribution. So then we can say this probability, by the definition of a discrete distribution, it's exactly 1 over n xi less or equal than C. So you see, we can reach the same formula, but from this different understanding. Okay, so basically, the V statistic, in short, is about plugging for a statistical functional, plugging the empirical CDF to replace the true CDF to come up with an estimator. That's the basic idea of the V statistic. It's very reasonable, very intuitive. And you see that by having this plugin idea, we can generalize a lot of estimators for a lot of parameters, as long as the parameter can be written as a statistical functional of the true CDF. Okay, let's look at two other examples. Second example is if I define my statistical functional to be the quantile. Okay, for some p in 0, 1. Okay, we defined this already, right? The quantile. Then we know what is the statistical functional applied to the empirical CDF. It will actually be, you can see, it's actually equal to what we defined before. This order statistic, that will become the sample quantile, and that will actually be the estimator of the population quantile. So if you think about why we are taking the ceiling, you can see it immediately from this definition. So if I remind you again, it's the nth of x such that P is less or equal than Fx. Okay. So if you replace everything, then this F is going to be replaced by the empirical CDF. And having the empirical CDF less, greater or equal than P is essentially, you can see it's actually essentially here. You're taking this N times P. That's actually where you should be at for that P probability. That's where you should be at. But if this happens not to be an integer, you would rather make the order bigger. So you take the ceiling. And that's actually consistent with this less or equal than notation. Okay, you can verify this later, but that's the reason. Okay, the third example for the statistical functional is expectation. So if we define this to be the expectation of y for y following f. So this notation is consistent with this notation pf. When we give this subscript, put the CDF as a subscript of the probability notation or the expectation notation, and later we'll have a variance notation here, or the variance notation. We basically mean that this random variable y follows this distribution f, and we're going to take the expectation or variance of y. So these two statistical functional can be called the mean and the variance functional. Okay, so then you can see if I do the plugin for the empirical CDF, it's this. And now y follows that discrete distribution at n values, x1 to xn, with equal probability. By definition, this expectation is exactly this, right? So we are not violating anything. We're just replacing doing plugin. Or if you think about the variance of n hat y, okay, and in that case here, this will actually give me 1 over n xi minus xn bar squared. Because for this y following empirical CDF, now its population mean is xn bar, right? And each xi is one of its possible values. So we're following the exact definition of variance for the population f and hat. So now you see, naturally, we're going to have 1 over n here instead of 1 over n minus 1. Okay, so these
Professor?
Yeah.
Are we considering that the functionals go to the extended real line, or just we're not worried about that right now?
We're not worried about that right now, right? When you say extended real line, you talk about the two infinities, right? Yeah, I think we don't talk about that, because you see here, if the functional maps to infinity, it basically means that that parameter is not defined. It's not well defined. So we do not bother to estimate it.
Okay,
yeah.
Thank you very much.
Yeah, no problem. Okay, yeah, so these are examples. And so let me conclude that. So the V statistic is basically, they are generalizations of sample moments. And they are actually defined as some statistical functional of some statistical functional evaluated at the empirical CDF. But we do have some requirement for the type of statistical functional. So we are going to say that we call this as the expectation functional, for T being the expectation functional. Okay, so our next definition will be, what do we mean by expectation functional? So here the generalization also means that we're not restricted to having the expectation defined by only one random variable. We can make this for m random variables jointly. Okay, so yeah.
Can you show the
Any
top
questions?
last piece of code?
Hello. Okay, so let's continue. Now we are going to give you this definition. So think about, we have m random variables from a distribution, IID from a distribution. Okay, so let's say y1 to ym, they are IID from a distribution f, any general distribution f. Then we can define a functional of f as the expectation of some function g. Let's say I have a function g that maps from Rm to R. Okay, so if I put in y1 to ym as the m arguments into my function g, and then I take the expectation, joint expectation for all y1 to ym, because they follow the same distribution f. So I write a only one f here. Then that result is what I define as a functional, statistical functional. So still, you see, this statistical functional, consistent with our definition, it maps a CDF to a real number, and the real number is the expectation. Okay, then how do we estimate it? So one thing we can actually think of it is something very interesting. So if you think about some permutation across the y1 to yn, so think about permutation, define y as a permutation on this set 1 to m. If I define pi as such a permutation, then how many pi's do I have? M factorial. So I have a total of m factorial pi's, right? I have so many permutations. And one thing you can think of is, since the y1 to ym are IID, a very important property is that, so they are basically exchangeable. In other words, the expectation f g y1 to ym would be equal to the expectation after permutation. So I write this as pi y pi 1 to y pi m. It will still be the same expectation. This is reasonable because those are IID. So you change their order shouldn't change the expectation. And this has nothing to do with G being symmetric around its M arguments or not. It's this symmetry, this result is simply from the IID of YIs. And here we're taking expectation, right? Expectation means what? It means that we are averaging all the possible values of each yi. So then they are the same. But if I don't take expectation, of course, they're not the same, right? For each particular realization, after permutation, the G function value will change for sure. But with expectation, that means that you take all the possible values of each yi into consideration. Then the IID will make the expectations equal. Okay, so because of this, then we could actually define a G star function. Think about it. So if I define a G star function, G star still have arguments, right? Now let me just call the arguments by lowercase y1 to ym. Here, they're just arguments. They're not referring to random variable or anything. They're just m arguments. I can define it as m factorial summation over all pi of g y pi 1 to g to y pi m. So it means that I take my original g, I shuffle or permute the m arguments over all possible permutations. For each permutation, I evaluate the value of g, and then I take the average of the m factorial evaluations. I define this as a new function, g star. And clearly, you see, then the g star is symmetric about its m arguments, right? By the definition, it's symmetric because I already consider all the permutations. And one more thing is that you can see also, now let's come back to our IID random variables. The expectation of G at y1 to ym is actually equal to the expectation of G star at y1 to ym. And this is because of this property, because of the star, because of star. I have this. So after I redefine the function G star, the nice thing is that it has the same expectation as my original G. With this, then I can say without loss of generality, I can assume the G to be symmetric. Because after I create the symmetric version of it, the expectation doesn't change. So why not just assuming G to be specific, to be symmetric? So without loss of generality, we assume G to be symmetric in the definition of TF, in this definition. The reasoning is, again, I misstated. The reason is that if G is not symmetric, we can create a symmetric G star. And with a symmetric G star, the TF, the expected functional, remains the same. Okay. So that's how we are going to define the expectation functional. So now formally, definition, expectation functional. Okay, so first of all, we need to have an integer m greater or equal than 1. And we have a function g that maps from Rm to R, and g is symmetric about the m arguments. M arguments. Okay, and we have y1 to ym, IID from a distribution f. Okay, then we call the functional defined on f, the functional of f, defined as the expectation of gy1 to ym, where they follow IIDF, and is the expectation functional. So now you see why this is a generalization of sample moments, because this G can have many forms, right? And the sample moment is just a special form. So think about what is a sample moment. Sample moments are special cases. For example, think of TF as the expectation of y to the power k. Okay, if this is what we define the the moments, sorry, I should not say sample moments. Moments are special cases. So this is the kth moment, and you see what is that? This is actually the special case. This is the special case where m equals 1. We only have one y following f, and the gy is equal to y to the power k. That's the g. So you see, this is a special case of that. Okay, and furthermore, for m equals 1, the expectation functional has another name, a special name as linear functional. So it's actually a linear functional. So let me say when m equals 1, the expectation functional is linear. So, linear always has the same definition no matter what context we're in. So linear functional means what? So it means if we evaluate this functional at the, let me say, a linear combination of two distributions, let's say alpha f1 plus 1 minus alpha f2. Okay, and alpha is between 0 and 1. So by the definition of expectation functional with m equals 1, let's look at it. It's actually the expectation. Now the distribution is alpha f1 plus 1 minus alpha f2. Expectation of gy, just one y. Yeah, there's no m, just one y. And still using g. And this is what? By the definition of expectation. And this is a mix, you can say this is actually a mixture distribution, right? Mixed from F1 and F2. So we know that by the definition of expectation, it's based on integration. So we can actually write this as the integration of gy. Okay? And the probability measure here becomes d. We write it alpha f1 y plus 1 minus alpha f2y. Okay, now I can use the linearity of integration to separate them into two integrals. So in other words, I can write this as alpha integration gy df1y plus 1 minus alpha integration gy df2y. This is by the linearity of integration. And then you see, this is essentially alpha ef1 gy plus 1 minus alpha ef2 gy. Okay? And then coming back to my definition of expectation functional, this is alpha tf1 plus 1 minus alpha tf2. So I show the linearity. That's why here we have the linearity for the expectation function. Okay, so now we have formally defined the expectation functional, and now we can have the V statistic formally defined. So how do we do it? It's basically the expectation functional, but using the plugin Empirical Cdf. Okay, so for expectation functional defined as TF, EF, G, y1 to yn. Given this expectation functional, the V statistic, we write as Vn, so we carry the sample size over, is defined as T at Fn hat, the empirical Cdf of x1 to xn. Okay, so Fn hat is the ECDF of x1 to xn. So then, by definition, this is expectation Fn hat of gy1 to I wrote it wrong, ym. So here the m has nothing to do with n. N is the sample size. M is the number of arguments in your g function. So m is only related to the definition of the statistical functional and has nothing to do with your actual sample, but n is your sample size. So now you see in the V statistic, we have both n that appears in the ECDF as well as m that's in the argument. Okay, so now the key message comes. What does this mean? So recall our discussion about m equals 1. That is, we only have one y in the g function, and that y follows the empirical CDF, which means that it takes a discrete distribution with n values, and each value has probability 1 over n. And now we have n such random variables IID from Fn hat. So now you see y1 to ym, they are IID from Fn hat. What does that mean? Each of the yi can take n values with equal probabilities, and those m yi's are independent. So how many possible values of y1 to yn can take? We can actually calculate it because this is a discrete distribution with only n values. This one can take n values, this one can take n values, this one can take n values. So the total would be n to the power m. That those are the all possible values y1 and ym can take, right? So y1, ym jointly has n to the power m possible realizations or values, unique realizations. So we can enumerate that, right? And each unique realization with equal probability. With equal probability. That's the key message. So you see that the Vn, by this definition, we can write it as the average across those n to the power m possible unique values. 1 over n to the power m, and we have the summation I1 from 1 to n. I'll explain. Im from 1 to n. G xi1 to xim. So here, I'm just using the I1 and Im to indicate the corresponding index of the one. So for I1, it's the corresponding index of Y1 corresponding to which index is among the X1 to Xn. So I refer that to Xi. So the value, the particular value I draw from X1 to Xn. And In is the index of the particular value Ym draws from X1 to Xn. So here, these are indexes in X1 to Xn. So they vary from 1 to n. So this is an expression to just enumerate all the possible values Y1 to Ym can take. And that's it. Okay, So this is the formal definition of V statistic. And you see, it's very interesting that even though in our general discussion, when we discuss statistical functionals, we have to rely on the general random variable notations y1 to ym, right? That can make our discussion very consistent. But ultimately, when we come down to the statistical functional evaluated at empirical CDF, and that's our definition of V statistic, we can rewrite it back based on our sample, x1 to xm. So now you see the final expression is only based on the sample. The intermediate random variable notation can be erased. Okay, and this looks quite complicated, right? But if we only think about m equals 1, the simple case, it's very easy. Then the Vn is simply 1 over n, and we only have one summation that is needed. I go from 1 to n, g x I. Okay, so you see this is clearly a plugin or sample version of the expectation functional, right? So this is an estimator of TF that is defined as expectation of f of g gx. Okay, we can write it because here x follows f distribution. So now you see this is an estimator of that, very obvious. Okay, so we have the V statistic definition, and this is the key message. Okay, now the question is, when m is greater than 1, you know, here m equals 1 or m greater than 1 is a totally different thing. It's a totally different thing. And so here we want to ask the challenging question. When m equals 1, is Vm an unbiased estimator of TF? That's the question we want to ask. Oh, and I forgot to say, another way to help you understand what's a statistical functional is to think of statistical functional as some parameter or property of the distribution f. So when we map the distribution f to a value, you can think of that real value, the output of this t, as some parameter like the quantile, like the mean, like the variance, or some other properties about that distribution f. So this can make the understanding of statistical functional more intuitive. So clearly, when m equals 1, the expectation of Vn is just Tf, right? That's obvious. Expectation of Vn here is just Tf. So this is unbiased for m equals 1. But for m greater than 1, is it still true? Not necessarily. The reason is here. If you think of the definition of Vn, we may have the same x1, say the same xi, some xi being selected for more than once in the arguments of G. So in that case, you violate the assumption that here the arguments y1 to ym must be IID. If they happen to select the same xi, then the IID is violated. Okay, the answer is no, because if, let's say that xi1, because if okay, I1 to Im have duplicates, okay? So let's say I1 equals 1, I2 equals 1, if that happens. I1 equals I2 equals 1. They both tend to select, they both happen to select X1. Then XI1 to XIM are not IID. That's the issue. And then the expectation, of g xi1 to xim, let's say this, okay, is not, may not, so this may not be equal to expectation of f at y1 to ym, where y1 to ym are IID from f. But in some special cases, you may still have equality if the G is some special form. That's possible, but just in general, it's not equal anymore because here some arguments are duplicates. Okay, so then let's look at one example to help you understand what is really happening. Okay, so in this example, we will have n equals to 2. Okay, and the g function, gy1, y2 function, is defined as the absolute difference between y1 and y2. So based on this, we can define an expectation functional. So TF defined as expectation of f g y1, y2. Here, y1, y2 IID from f is expectation f y1 minus y2. Okay, that's the definition of the expectation functional. We haven't touched our sample yet. Now we give our sample. A random sample x1 to xn IID from f. Okay, so the V statistic, Vn, let's realize what we said. N equals 2, so it's n squared. And here is I1 from 1 to n, I2 from 1 to n. And it's the G of y, xi1, xy2, right? So it's let me just write one more step, xi1, xi2. This is following what we said before. Now let's use the G. N squared, I1 from 1 to n, I2 from 1 to n, xi1 minus xi2. That's my V statistic. Now let's do the calculation of the expectation. Okay, so here we have y1, y2, IIDF. This is key. So you see, when I do expectation of Vn, I must separate this term into two cases. One is that I1 doesn't equal to Y2. In that case, xi1, xi2 are indeed IID. Okay, I need to make expectation here. Okay, I need an F, here. And the first summation is I1 doesn't equal to I2 and xi1 minus xi2. And the second term is I1 equals I2. So when they're equal, then there are n such cases, right? So I1, let's put I1 from 1 to n. And I2 equals I1. So this is xi1 minus xi1. So clearly, the second term is 0. I don't need to worry about it. And I only have the first term to worry about. And I can get expectation inside since xi1, I2 are IID, and x1 to xn are IID. So I just need to count how many terms are here. And the expectation of each term is equal. So how many do I have here? Not equal. It's actually n times n minus 1. There are so many things. So basically, I would actually have n times n minus 1 over n squared expectation of x1 minus x2, right? Because they're IID, I can write x1 minus x2. And this is actually equal to my TF. And I can cancel 1n. So I get n minus 1 over n times TF. So you see, it's biased. It's not unbiased because here it's not equal to TF, but equal to this. So I conclude that Vn is biased. Although it's not asymptotically biased. Asymptotically, the bias goes down to 0, but it's biased. So the bias correction is for a finite n. And here we already see some intuition for doing the correction, right? So you would say, okay, how about in my definition of Vn, coming back here, what if I just remove the duplicates? I only keep the cases where I1 and In are all unequal. Yes, that's exactly the definition of U statistic. Okay, so we will conclude with the definition of U statistic for today's lecture. So to make Vn unbiased, we remove duplicates in I1 to In. Oh, and furthermore, the reason why we teach you this is because understanding the statistical functional is essential for you to understand the bootstrap theory. Although I guess that we may not have time to cover bootstrap this quarter, because we're actually doing slower than we usually did when we do this in person. But I think this will give you the foundation. So if you are interested, we can still share we have the bootstrap notes from past years. You can still read those and you will see why bootstrap is connected and how we can understand bootstrap from the perspective of statistical functional. Okay, so yeah, so now let's look at the Use statistic. So here, by removing duplicates, we can actually add a requirement by requiring, okay, all the I1 to Ym are not equal. We can also just consider a unique set of I1 to Im. So we can make sure they are strictly increasing. I can require this. So for any unique n values picked from 1 to n, I can always order them, right, from the smallest to the largest. And based on those, we define the U statistic. Okay, so U statistic is defined as UN as how many such n can I pick from n? It will be n choose n. So I have so many possible unique n values to be chosen from, 1 to n. And I still have the n sum, but what I require is that my I1 is less than In, less or equal than n. I need to choose those in this order, and then I evaluate xi1 to xin. So it's basically the same as the V statistic, except that we remove the duplicates. That's the whole idea. And then we can easily show, now because they're all different, then they're IIDs, right? So we can easily show. So obviously, the expectation of UN when xi1im on x1 to xm follow f is equal to TF. which is defined as the expectation of f of g y1 to ym. Okay, so we achieved the unbiasedness. All right, so we will conclude here, and we will not have a lecture on Thursday because of the Thanksgiving holiday, and then we will resume on next Tuesday. Okay.
Professor, so do you have time for me to ask a question about this?
Okay, sure, go ahead.
So in the expression of the V statistic, I think we could use like basic combinatorics to show that asymptotically, as like n gets large, you know, the coefficient on, we could break the sum into like sums where one pair of terms is equal, two pairs of terms are equal, etc. And we could maybe show that like asymptotically it is all the types of subsets of terms with repeats sort of become less and less important as n grows, and because like the in the, you know, n choose m terms, you would, or n choose k terms, like the numerator would have a lower than n. Okay, so that's why like the 1 over n variance estimator is like okay asymptotically. Is there some, are we going to talk about this?
We're going to talk about, our next topic is going to talk about the asymptotics of the Use statistic. Okay, so the Use statistic, we're going to talk about it, but you can see that here we also have some complication for the Use statistic. That is, if you think about the summation of n choose n terms, there are some, like it's the same x1 to xn that get involved in those n choose n terms. So those n choose n terms, n choose m terms are not independent. So we cannot directly apply the central limit theorem, right? Because that requires the summations over independent terms. So how do we deal with it? We are actually going to talk about something called H projection. In other words, we're trying to make the summation independent, conditionally independent in some way. And then we'll derive the asymptotic distribution for the U statistic. And then for V statistic, as you said, we can actually show that the V statistic is equal to the U statistic plus some other terms, that those other terms will go down to 0 as n go to infinity. So that's why if we talk about asymptotics, then U statistic and V statistic have the same asymptotics.
Okay. Yeah, just because the bootstrap seems so much more related to the V statistic. So I'm thinking.
Yeah. Exactly. Bootstrap is related to the V statistic. Yeah. And if we're talking about a large sample, right? Asymptotic, when n is very large, that's exactly what we mean by asymptotics. When n is very large, then it doesn't matter whether you use V or U, right? But if n is small, then this bias correction is important, such as for the sample variance case.
Okay. Thank you very much.
Yeah, thank you. Yeah, that's a very good question. Yeah, and that's why I would say the Use statistic concept is very important in old days. I think it was like proposed, I think V statistic was proposed in 1940s, and soon people have this. So at that time, n is very small and bias correction is very important. Yeah. Okay. So thank you for the question, Zach, and I'll see you on next Tuesday.